velocity on a circle. Okay, suppose I were to stand with my arm out to the side and then rotate my arm until it was right in front of me. When I do that, my fingertip moves along a circular pathway where my shoulder is the center of the circle and my arm is the radius. Watch again, my arm is rotating around 1/4 turn, my fingertip along the edge of that circle. Here's the question we want to answer. How fast was the tip of my finger moving if I made that 1/4 turn in half a second and my arm is 30 inches long? Well, there's two ways that we can answer this question. The first one is called angular velocity. Velocity is another word for speed in our context. The definition of angular velocity, we use the Greek letter omega, which looks a lot like a W, for angular velocity. Omega equals, and it is the change in the angle, which I'll call theta, divided by the change in the time, which I'll call t. Omega equals theta divided by t. Well, let's try out this formula in my situation. So for me, the change in my angle would have been 90 degrees. I made a 1/4 turn, and my time was half a second. I'm putting the units on here so that we can see our units clearly in our final answer. To simplify this, if I multiply the top and bottom by 2, then what I end up with is 180 degrees per second. That would be my angular velocity, 180 degrees per second. In radians, this would be pi over 2, right, is 90 degrees. So pi over 2 radians over that same half a second. Again, multiplying the top and bottom by 2 works out nicely. All the 2's cancel. And I'm left with pi radians per second. Or, as a decimal approximation, about 3.14 radians per second. That's one way to answer the question, how fast was the tip of my finger moving? Another way that we could answer that same question, though, would be to use what's called linear velocity. Linear velocity, or linear speed, is abbreviated with the letter v for velocity, and its definition is the change in the distance, which I will call s, over the change in the time, which we will once again call t. So v equals distance divided by time, s over t. Now, let's think about my situation. Here's a visual. If you picture this corner as my shoulder, and here's the starting position of my arm with my fingertip out here at the end, I rotated around 1/4 turn until my arm ended up in front of me. So the distance my fingertip traveled is the length of this arc. Well, we have a formula, don't we, for the length of an arc. It's s equals r times theta, as long as theta is measured in radians. So in my situation, the radius would be the length of my arm, which we said was 30 inches. The angle is that 90-degree angle, except we have to use radians, so that would make the angle pi over 2. When I simplify that, I end up with 15 pi inches. Okay, now let's calculate the linear velocity. The velocity is the change in the distance, which we just calculated to be 15 pi inches, divided by the change in the time, which we've known is half a second. I'll multiply top and bottom by 2 to simplify. And what I'm going to end up with here is 30 pi inches per second. Or if I grab my calculator and type in 30 times pi, I get about 94.2 inches per second. That's another way to describe the speed or velocity of my fingertip. It was traveling at 94.2 inches per second. Now, I know what you're asking. Is there some kind of connection between these two velocities? Absolutely. Take a look. Here was our formula for linear velocity. V equals s over t. S is the length of that arc along the circle. T is the change in the time. Well, as long as we work in radians, we know that S, the arc length, is equal to r times theta, the radius times the angle. If I then separate this into two pieces, I could write it r times theta over t, right? Imagine me putting a 1 underneath this and multiplying across. I'd get right back to here, r theta on the top and t on the bottom. So that was a perfectly valid move. Well, theta over t, haven't we seen that somewhere before? Yes, theta over t is omega, the angular velocity. And so this becomes r times omega, leading me to this wonderful formula. The linear velocity is equal to the radius times the angular velocity. It is a wonderfully simple formula, but because we relied on S equals r theta, it only works if the angle is measured in radians. You can check it easily for the arm rotation problem. We had said that my angular velocity was pi radians per second. To get the linear velocity then, all you have to do is multiply your angular velocity by the radius. The radius was my arm length, which was 30 pi inches per second. That's exactly what we got. So this relationship works every time. Aren't radians great? Thanks for watching.